Let's continue with the chapter electrostatic potential and capacitance. So here we are going to see the electrostatics of conductors. This is actually a summary of what we have learned in chapter 1 and chapter 2 till now. So inside a conductor, the electrostatic field is zero. This we have proved with the help of Gauss's law. In the case of a spherical shell, we have proved that inside it is zero. And at the surface of the charged conductor, the electrostatic field must be normal to the surface at every point. That also we mentioned there. Wherever you are taking the electrostatic field, it should be the direction is taken to be perpendicular. It should be normal to the surface at every point. And interior of a conductor can have no excess charge in the static situation. And
electrostatic potential should be constant throughout the volume, and it will be having the same value as what is inside. It will be the same like what is inside. And the electric field at the surface of a charged conductor is given by E is equal to sigma by epsilon 0 into n. This came from the spherical shell derivation. When you have done, the electric field of the spherical shell is given by E is equal to sigma r square by epsilon 0 r square into n. This was the equation. In here we have given the expression. Here we have substituted r is equal to r. So when we have substituted that, we got electric field as sigma by epsilon 0 into n. So that is the value which we have written here. The electric field is given by, at the surface, electric field is given by sigma by epsilon 0 into n. And last topic is electrostatic shielding. When we have said about the spherical shell, inside the spherical shell the electric field is zero. We have discussed there. Then I have explained about sitting inside a car. When a thunder or a lightning is there, it is safe to sit inside a car. That we have already said that inside a cavity, this electric field inside in a cavity, electric field inside a conductor is zero. That we have said. A charged conductor inside the spherical shell, it is zero. That we have already seen electrostatic shield. So these are the electrostatics of conductors. Next we are going to learn about the dielectric. So dielectric means it is a non-conducting material normally. So dielectrics and polarization we are going to see. This is also important, and this is needed for our next coming topic, that is capacitors. So we are going to see what is the behavior of a dielectric when it is placed in an electric field, and we are just going to compare the behavior of a dielectric and a conductor. So dielectric. Normally it is a non-conducting material, or we will say that number of charge carriers are less compared to a conductor. In a conductor, you know that if you are taking a conductor, just think that this is a conductor. In a conductor there will be so many free charge carriers. So here I am going to apply some electric field. This is the electric field which I have applied. So because of the electric field, you can see that the charges will align. It will be like, and all positive will come like this. So an external electric field is applied, that we just mark it as E0. Because of the external field, you can see that all the negative are coming to one side, all the positive are coming to the other side, and an electric field is induced in this conductor, and that electric field we call it as induced electric field. And when you are adding these two, external electric field and the induced electric field, the total will be equal to 0, or induced electric field is just compensating with the external electric field. So we can write, this is the direction of applied electric field, and this is the direction of induced electric field, and you can write E applied plus E induced will be equal to 0 in the case of a conductor. So this is the case of a conductor. Now we will see if a dielectric is taken, what will happen. Okay. So here in the case of a dielectric, an external electric field is applied. That electric field is in this direction, as we have already said. The free charge carriers are less in number. So, here this all the negative will be aligning, all the positive also will be aligning. But an induced electric field is generated in the opposite direction of applied field. We call it as E induced. But E induced will not cancel out the applied electric field. So in the case of a dielectric, if you are adding the applied electric field and the electric field which is induced in the dielectric, it will not be equal to 0. So that is the specialty of a dielectric. It will be having some electric field. It will not be equal to 0. Now we have discussed about polar molecules and non-polar molecules. In non-polar molecules, example also we have seen. Now how it will behave in the case of electric, if an electric field is there and if an electric field is not there, what will happen, we are going to see. So first we will see for non-polar molecules. We have seen some polar molecules examples like oxygen, hydrogen, etc. And these non-polar molecules, the centers of positive and negative charges coincide. So there is no permanent dipole moment for the case of a non-polar molecule. So that we have already seen. And in the case of a polar molecule, but the centers will not coincide, and it has actually a permanent dipole moment, and when we are applying an external field also, this will separate the positive and negative charges, which induces a dipole moment in the polar molecules. So here we are going to see a non-polar molecule, how it will behave when electric field is not there and when electric field is there. So first we will see when electric field is not there. So this is the case of a non-polar molecule. When electric field is not there, both the positive and negative, you can see that it will coincide. So centers of both positive and negative will coincide when electric field is not there. Electric field is not there. E is equal to 0. Now if we are applying an electric field to this type of material, what will happen, we will see. So here we are going to apply an electric field. So electric field is not equal to 0. So we are going to apply an electric field. This positive and negative centers will be displaced, or it will be separated. So here a positive and a negative, positive and a negative. Now these are separated. You can see these are separated. So this is the case of a non-polar molecule when electric field is not there and when electric field is present. Now we will see the case of polar molecules. Polar molecules are the ones in which even in the absence of electric field, these are having some dipole. Dipole means positive and negative are separated by a small distance. So here we are going to see the case of polar molecule. For the case of a polar molecule, if electric field is not there, then also this molecules will be separated by a small distance. So here you can see that even in the absence of electric field, the centers of positive and negative are not coinciding. It is having some dipole, but this dipole will not be in a proper oriented in a proper direction. It will be randomly oriented. So here and there it will be. So the total dipole moment, if you are taking as it is randomly arranged, total dipole moment will come out to be 0. So here we are going to see now electric field. When the electric field is applied to a polar molecule, what will happen? We are going to see. This will arrange in the form of in a proper way. So it will try to align in a proper way when we are applying an electric field. Here it is E is not equal to 0. So this is the case of polar molecules when electric field is not there and when electric field is present. Now we are going to take a dielectric slab, how it will behave in the case of when we are applying the electric field. We are going to see a dielectric in the presence of electric field. We are going to see. So here we are going to take a dielectric slab which is having a thickness. Okay. So this is a dielectric slab, and this dielectric slab is having both positive and negative. Each one we are just going to represent. So here 1 minus. So this is the case when we have applied an electric field in this direction. So here you can see at this end, all this are negative. This side is fully negatively charged. Now this plus and this minus will be neutralizing. Again here plus and minus will be neutralizing. Plus and minus will be neutralizing. And at this end of this here, you can see that all the positive will be in one side. So when we are applying an electric field to a dielectric, you can see that this part fully it will be negative. So here a surface charge density, here we can say sigma minus sigma due to polarization. So minus sigma p will write. Surface charge density is developed. Here it is fully positive, so we can write plus sigma p is developed due to polarization when we applied an electric field to a dielectric. So this is needed for our next topic, that is for capacitor. We need to remember what is a dielectric and what will happen if electric field is applied to a dielectric. We have to see.